In this lecture, I will expand an idea that I have already mentioned the previous time, that one should be able to construct solutions of initial value problems graphically. So to this end, let's suppose that we have this ODE y prime equal to f of x y. And notice something that I've already mentioned last time, that what this ODE gives you, it tells you that if you are sitting at a point x, y on the plane, then the ODE prescribes the slope of a tangent line of a curve, y of x, that passes through this point xy, right? Because y prime is the slope of a tangent line. So then, wherever your function f is defined, you know the slope, what the slope is. And if you do know what the slope of a tangent line is, then at every point you can draw a short line segment which will represent a curve that passes through the point xy. Now, once you draw this field of lines on xy plane, then you end up with something that is known as a direction field. And then we can use these direction fields to figure out how solutions of initial value problems look like. And let me demonstrate this on several examples. And so example one is going to be fairly simple. I want to sketch a direction field of an equation y prime equal to x. And then I want to use this direction field to solve the initial value problem here. So it's the same equation y prime equal to x, now supplemented by the initial condition y of 1 is equal to 1. All right, so let's see how we can sketch the direction field. First of all, we need to draw the set of axes on xy plane. And then let's do this. Let's pick a point. In fact, the initial point in this initial value problem is a point where x is equal to 1 and then y is equal to 1. So at that point 1, 1, let's say it's somewhere here, the slope must be equal to 1, so it is going to be 45 degrees. So that's a short segment of a tangent line at the point 1, 1. Now, if we continue in the same way, so actually let me plot one more point. So what about the point minus 1, 1, which will be symmetric to the point 1, 1 with respect to y-axis. So what is going to happen at that point? Here x is equal to minus 1, y is equal to 1. So it doesn't matter what the value of y is, as long as x is minus 1, then y prime should be minus 1 as well. So that means that if my curve passes through the point minus 1, 1, then its slope must be minus 1. So I draw a short segment at this point, and it should look like this. All right. So if I want to plot, to sketch the entire direction field, then I would have to sketch these directions at many more points. And certainly it's not going to be very efficient to start selecting these points randomly, because there would be a lot of points that I'll have to select. And in fact, maybe I'm not going to select them in a reasonable way, so I'll miss some important features of the direction field. So instead, what people typically do, you want to determine the set of points where the slope is equal to some constant. So, for example, let's say we want to find all points. So I'm looking for some systematic way of producing this plot. So I want to find all points where y prime is equal to, let's say, 1. Okay, but then I know, so since y prime is always equal to x, then what I'll have is I want y prime equal 1, y prime is equal to x, and so x is equal to 1. Now, what is a set of points corresponding to x equal to 1? That is a vertical line through x equal to 1, right? Because this is a set which consists of all points with x coordinate equal to 1. Okay, so I have a vertical line through x equal to 1. And now, what do I know about this line? I know, let's see, let me fix this. Okay, this looks more vertical. What I know about this line is that at all points on such a line, what should happen? Okay, let me try to fix this. Jeez. Sorry. So at all points on this line, what should happen is that whenever a solution curve crosses a line like this, then its slope must be equal to 1. So here the slope is 1, here the slope is 1, here it is 1, here it is 1. Let me just make this better. Here the slope is 1, so everywhere on this line the slope is 1. Okay, just likewise, what about all points where the slope of a tangent line must be equal to -1? So let's write it as b. All points where y prime is equal to -1. Again, since y prime is equal to x, that means that -1 must be equal to y prime equal to x, so x is equal to -1. What is x equal to -1? Again, that is a vertical line now at x equal to -1. So let me try to sketch that. Okay. And so everywhere on that line, slope must be -1. So let me attempt, to draw this. -1, -1, everywhere here. Okay, so then from this, we can actually see that if I want to find all points where y prime is equal to c, and that is a constant, then I'm looking at all points, so looking at all points where x is equal to c, right? Because y prime is always equal to x. And so those are the vertical lines. So, for instance, if I'm looking at x-axis, at y-axis, sorry, then on y-axis, what do I know? I know that x is equal to 0, right? So y-axis corresponds to x equal to 0, and when x is equal to 0, then the slope, x is equal to 0, the slope of a tangent line is 0, so the direction field on x-axis will be horizontal. Everywhere, if a solution curve crosses x-axis, it must be horizontal. And let's do a couple more of these. At x equal to 2, so a vertical line at x equal to 2, what happens there? X is equal to 2, that means that y prime is equal to 2, so we get slopes 2. So again, the same slope everywhere on this line, but now the slopes are steeper than at x equal to 1. And similar to this, if I look at x equal to minus 2, x equal to minus 2 means slope is minus 2, so all curves are going to be steeper on this line. Steeper and will have a negative slope. So they're all pointing down and to the right. All right, so then the direction field of this equation looks like I have just plotted here. And let's say I want to reconstruct now the solution curve that corresponds to my initial value problem as drawn here. How would I proceed? So I'll start at the point 1, 1. So what I know about the point 1, 1 is that, let me redraw this in the purple, that a small piece of a tangent line that crosses the line x equal to 1 is going to have a slope 1. And so that would be basically a piece of my solution curve that goes through the point 1, 1. Okay, so if I move a little bit to the right, along this curve I end up at a point like that. What happens at a point like this? The slope is given by the x value at that point, which is now slightly larger. So again, I use a direction field here to draw a piece of a solution curve. And then I can continue this way, end up at a point here, I get a piece of a solution curve, I end up here, draw a tangent line which is a piece of my solution curve, and I continue like that and I end up with a graph like this. If I move in the opposite direction, then the slope gets smaller. Eventually you'll intersect y-axis where the slope will be 0. You continue drawing these small short segments of a solution or small segments of tangent lines. So you end up at this point, so the slope here is minus 1. Keep going, slope is slightly larger, keep going, slope is even larger. And so then what happens is that graphically we reconstructed a solution, and it looks like this. But clearly, right, that solution in this case we can find analytically, so we can verify if our approach is actually working. So if we try to verify it analytically, then what do I know? I know that y prime is equal to x. So if y prime is equal to x, this implies that y is equal to the integral of x dx, which in turn is equal to x squared over 2 plus a constant. And then we have the initial condition, y of 1 is equal to 1. So 1 is the same as y of 1, which is the same as this function evaluated at 1, at x equal to 1. So which is 1/2 plus c. So c must be equal to 1/2. And I do have the explicit solution of my initial value problem. So c is equal to 1/2. So therefore y is x squared over 2 plus 1/2. And indeed, right, the graph that we constructed is a parabola. So that means that we graphically reconstructing a proper solution of the initial value problem. Now notice that I can do this starting from any point on the plane. I can use any other point as an initial point, follow this procedure, and I'm going to reconstruct the solution curve again. All right, so let's try to do another example. Well, let's say I want to sketch do basically exactly the same thing. I want to sketch the direction field of now a different equation, y prime is equal to minus x over y, and then use that to solve, use that direction field to solve this initial value problem, starting from the same point. Okay, so follow the same logic. We are going to draw the set of axes first. Okay, y-axis and the x-axis. And once again, I hope that you see that in this case I do want to follow the same strategy rather than trying to sketch slopes of tangent lines at some random points. I'd rather find a certain pattern which I can then utilize to sketch the entire direction field. And so the pattern would work in the same way. I want to find all points. So to accomplish this task, I need to find all points where y prime is equal to c. Now, where is y prime equal to c? Because y prime is minus x over y, I'm looking for all points where minus x over y is equal to c, right? So therefore, we want all points where minus x over y is a constant. Okay, and so when is minus x over y a constant? Solve this for y. So y is going to be minus x over c. All right. So if y is minus x over c, or else I can write this as minus 1 over c x. Well, this is y equal to a constant times x, and y equal to a constant times x, then what I'm going to get for each c the set of points is a line through the origin with a slope minus 1 over c. Okay, all right, so then for c equal to 0, what do I get? So actually, let's not start with c equal to 0, let's start with c equal to 1. So if c is equal to 1, c equal to 1, then y is equal to minus 1 over 1x, so y is minus x. If c is equal to 2, then y is going to be minus 1/2 x. If c is equal to 1/2, then y is minus 2x. And let's do some negatives here. If c is equal to, let me stick them here. If c is equal to minus 1, then y is x. If c is equal to minus 1/2, y is minus 2x. And if c is equal to minus 2, y is minus 1/2 x. Okay, so what this means is that what we will need to draw is a bunch of lines, and then on each of the lines, we will have a constant slope of solution curves. So let's draw those lines. If once again x is equal to, let's actually look at it from a slightly different perspective now. If y is equal to x, then the slope is minus 1. If y is equal to minus 2x, slope is minus 1/2. Y is equal to minus x, slope is 1. Y equal to minus 1/2 x, slope is 2, and so on. So what I will do, I'll draw lines, and then we will see what the slope is on those lines. So line is y equal to x. Something like this. Everywhere on this line, slope is equal to minus 1. Now, if slope is equal to minus 1, that's a negative reciprocal of 1. So the slope must be perpendicular. Slope of tangent lines or slopes of curves that pass through this line must be perpendicular to the line itself. So everywhere here, the slope is like this. All right. Okay, so then what about the line y equal to minus x? On the line y equal to minus x, c is equal to 1. So 1 is a negative reciprocal of minus 1. So we have the same story. I draw a line through the origin. And on that line, now the slope is 1. So 1 is perpendicular to the slope of a line itself. So this is a direction field intercepting a line x equal to minus 1. All right. Then we continue. Let me just add some more lines here. Okay, so then we continue. We look at y equal to minus 1/2 x. Y equal to minus 1/2 x is a line with a negative slope minus 1/2. but the slope of tangent lines that intersect that line is always going to be c equal to 2, which is negative reciprocal of minus 1/2. All right, so I need to draw a line y equal to minus 1/2 x. So it would be something like this. And then what do we see on this line? The slope is minus 2, or slope is positive 2, negative reciprocal of 1/2. So again, tangent lines will intersect this line in a perpendicular fashion. So this is going to be my direction field on that line. Well, let's see, c equal to y equal to minus 2x. It's the same deal, right? Y equal to minus 2x. The slope of that line, minus 2, is going to be a negative reciprocal of slopes of tangent lines that intersect y equal to minus 2x. So that means that, again, tangent lines to our curves must be perpendicular to the line itself. So y equal to minus 2x would have a slope which is larger, will have a slope which is larger than 1. So it is as follows. And then everywhere on that line, my direction field is perpendicular to this line. So it is like that. And so you see in this case what the pattern is. On any line that it passes through the origin, the direction field is going to be perpendicular to that line. So we can draw maybe one more, actually two more lines. Y equal to 2x is going to be like this. Let me redraw it. Oops. Y is equal to 2x. Actually, let's do three more. Y equal to 2x, y equal to x over 2. And we'll also look at both x-axis and y-axis. So for y equal to 2x, what have I got? All tangent lines must be perpendicular to this line, so I get something like this. And on 1/2 x, same idea. Tangent lines are perpendicular to that line. Now, what about x-axis? On x-axis, we are going to have that, let's see, so on x-axis, again, the tangent lines must be perpendicular to, because it's a line passing through the origin, tangent lines must be perpendicular. So even without writing anything analytically, I know that the field must be like this, direction field is like that. And on the y-axis, again, perpendicular. So it's going to look like that. Note one thing here, which follows from this calculation. If I look at the origin, right, all these lines intersect at the origin. So what happens there? There is no particular direction that you're going to get at the origin. So no particular direction at the origin. Okay, and now let's try to reconstruct or approximate the solution of the initial value problem. So that solution required that y of 1 should be equal to 1. So I start at the point 1, 1, wherever it is. So let's say it's going to be somewhere here. So I start at that point. I have to go perpendicular to the line itself. I'll end up on the next line. I draw another piece of the perpendicular of a line which is perpendicular now to this line that goes, so let's see, now that is perpendicular to this line that goes through the origin. I end up over here. Once I end up over here, I draw another segment, another short segment. I end up here, and I keep going like that. And what you see is that you're reconstructing a circle, right? So circle that goes through the point 1, 1. So what we find is that the solution, the graphical solution, seems to be a circle x squared plus y squared equal to 1. So can we verify whether this is true or not? So if I'm assuming that this is true, then I can always check, right? How do I check? I need to substitute this function into my equation. And this function specifies y of x implicitly, like we discussed. So let me continue here. So check. I will take an implicit derivative. So if I take implicit derivative, then I'll have 2x plus y prime equal to 0. And I solve for y prime, 2y prime. And if I solve for y prime, I'm going to get y prime is minus minus x over y. So this checks out, right? So indeed, the solution that I found, well, I check out actually one more thing that we need to verify. What is the, am I right here? So I got a circle, right? But how do I know that the right-hand side here is equal to 1? So I verified when I find the implicit solution, when I take the derivative of both sides of this equation, then 1 goes away. So in fact, instead of 1, I can put any other constant, and I will still get this expression as a result of implicit differentiation, which is my equation. So that means that I do satisfy that equation, but I have to verify whether or not I'm satisfying this boundary condition, this initial condition. And in fact, am I going to get 1 here or not? So I was guessing that I'm going to get a circle, and actually that circle passes through the point 1, 1. And if a circle passes through the point 1, 1, then actually its radius is not going to be 1, right? Because what should it be? If I substitute 1 for x and 1 for y, then I'm going to get 2. So it should be 2 here and not 1. That's a circle that goes through 1, 1, through point 1, 1, so its radius is actually square root of 2. Okay, so you see that actually this graphical way of solving things can be fairly powerful because we ended up with the correct solution just from graphical considerations. Let's try one more example before we move on. So let me actually formulate it in exactly the same way. So now instead of using this equation, let me modify it a little bit. Let's say y prime is equal to x squared plus y squared. Fine, so what can we do now? So again, following exactly the same strategy, what I want to do, I want to find all points where y prime is equal to a constant. Now, in this case, y prime is the same thing as x squared plus y squared. So I'm looking for all points. In fact, how about we do this? Where y prime is equal to, let's say, c squared. Because if c is a constant, then likewise c squared is a constant. So then I'm looking for all points where x squared plus y squared is equal to c squared. And those are circles of radius of radii. In fact, it's just a single circle for a given c. So a circle of radius c. Actually, notice one thing here. Because the slope is x squared plus y squared, it always must be greater or equal than 0. The slope cannot be negative. So c would be a number which is greater of or equal to 0. All right, so let's try to sketch the direction field. X-axis, y-axis. Okay, so we can have c equal to 0. If c is equal to 0, then we have a circle of radius 0. So that means that if we're at the origin, which is a circle of radius 0 center at the origin, then at 0, we're just going to have a slope 0. Okay, next, if c is equal to 1, I'm going to get a circle of radius 1. And everywhere on that circle, the slope is going to be 1. So, oops. Everywhere on the circle, slope is 1. Let me just fix something. Fix the colors. Oh well. Because I'm using blue to sketch the tangent lines. So everywhere on a circle, the slope of curves that intersect the circle must be plus 1. Then if I make c equal to 2, I get circle of radius 2. So let's, oops, circle of radius 2. That doesn't look like a circle. All right, so let's accept this as a circle. Circle of radius 2, the slope is going to be what? Slope is c squared. Therefore, the slope in this case is going to be 4. So things are going to be much steeper here. And so the conclusion from this, I'm not going to give to draw any more curves here. Let me just label these. That this is C equal to 2, and that's a circle of radius 2. This guy is C equal to 1. So the conclusion is C is bigger on circles of larger radius. The slope of tangent lines is going to be bigger on circles of a larger radius. Okay, and then if I want to reconstruct a solution of the initial value problem like this, I have to start at the point 1, 1. The point 1, 1 must be in a circle, on a circle again of radius square root of 2. So that would be somewhere here. Somewhere here. If I move to the right, then the slopes are getting bigger very quickly. And if I move to the left, the slopes are getting smaller. And then they're getting bigger again. So that is a solution curve of my initial value problem. Okay, so in this case, I don't really know exactly what the equation of that curve is, but I do know that the curve must look, solution curve must look like this. All right, so I hope that this gives you an idea of how to accomplish these type of constructions. And then in the next lecture, we're going to look at the specific example of equations where graphical way of solving actually will tell you a lot about how these equations behave.